For our very last topic in our course, we're going to talk about how to apply the calculus ideas that we already have developed to a function that has more than one variable. Comes from the fact that when you, again, if you imagine a surface, so imagine yourself walking out in the room and looking up and seeing a billowing parachute over your head. There is a sense in which you could say whether the parachute above you is steep or not steep or flat. But the problem when you have more than one variable is that the steepness of the graph can't really be described by a single number. The steepness depends on which way you're looking. It's possible for a graph to look very flat if you're looking sort of left to right, but if you're looking front to back, it could look very steep. So we have to think about measuring rate of change or slope in different directions rather than just having just one direction that we can go. So let's start off with the case that we know. This would be an example of a cost function where we have $100, say, in fixed cost, and we're manufacturing something that costs $500 each. And the idea here is that you have $500 times the number of things that you produce. So your cost is $500 times X plus your fixed cost. So in that case, marginal cost ought to really just be 500. Now we know the derivative of 500x is 500, so that does work out. But it makes sense in this very simple case that marginal cost is $500 all the time, because at any time, whether you've made one of these things or 1,000 of these things, for every additional item you make, it costs you $500 extra. And so $500 per item is our marginal cost, and that makes sense in that setting. So let's look at an analogous question in more than one dimension. Let's suppose that we make two things. One of them costs $70 each to make, and the other one costs $100 each to make. So if we make X of the first type, then it costs 70 times X dollars to manufacture that number. If we make Y of the second type, it costs 100 times Y to manufacture that number. And again, there's some fixed cost here, maybe that for paying your rent or whatever for that day that you have to pay no matter what. So this would be a cost function analogous to the other one in a situation where we make two different items. Well, if we want to find the derivative here, we're going to define two different sorts of derivatives. Do we want the derivative with respect to X or the derivative with respect to Y? So in other words, well, let's just say in particular, derivative with respect to X is going to mean that we want the rate of change of cost with respect to X, which means that we want the rate of change of X. We want to know how much cost changes for every 1 unit change in X. So that's what C sub X XY means. It means this would be dollars per 1 unit change in X. And so the key there is that we're ignoring the Y altogether. We're assuming that the Y's are fixed. What we're asking ourselves is, if we were to leave the Y's fixed, so if we don't change the number of competition boards that we produce, then how much does cost change when we change X by 1? And that's what this 70 should represent. $70 for each board for each standard board. That's how much additional cost we'll have if the only thing we change is the X by 1 unit. And then similarly, if all we do is change the Y by 1 unit, then we'll have $100 for every 1 unit change in Y. And so that makes sense as well. So we have two different derivatives. We have the derivative where we are keeping the Y fixed, so we don't change Y, but we think of the X as changing by 1 and we want to know how much cost changes. Or we can leave the X fixed and think about how much does cost change when the Y coordinate changes by 1. These are called partial derivatives, and when we're in the context of an application problem, these are the right ways to interpret the result. We have the change in the z coordinate in the output of the function, cost in this case, for every 1 unit change in X or for every 1 unit change in Y. So you will have problems where you have to interpret the results, and all you have to think about is which variable is changing, and in the numerator, what is the output of the function. So in this case, cost is the output, so that's the numerator, dollars, and if we're changing the competition boards or the standard boards, that determines whether, that's determined by whether we're differentiating with respect to x or y. So the formal definition looks like this, and I only included this so you could just sort of see that it's really not a different idea. Just like before, the h here is x plus h minus x. That's just 2 points close together, but you can see that we're leaving the y fixed. We're not changing the y at all. And so if I wanted to characterize this in sort of a simple way, the outputs of the f's are what we call z. So I would say this is a change in z, and down here I have x plus h minus x. That's a change in x. So all I'm doing here to find the derivative with respect to x is I'm measuring the change in the z-coordinate with respect to the change in the x-coordinate. Now remember that the z really is measuring the height of a surface, and so what we're really measuring here is the how fast or how high the surface rises for every 1 unit change in the x direction. So if I move parallel to the x-axis 1 unit, how much do I expect my surface to rise? And so that really will be a measure of steepness. If I have a partial derivative of 5, that means for every 1 step I step in the x direction, I expect the surface to go up 5 units. And so that's pretty steep. But if I see a partial derivative that's equal to 0, then that means that as I take 1 step in the x direction, the height of the surface hasn't changed at all. There's a 0 change. So we can visualize this with an applet. Oh, I guess we should find a derivative first. Yeah, so let's talk for a second about computationally what this means. It's a little hard to get used to, but you have plenty of problems here to practice. When we want to compute one of these derivatives, the secret is we first identify that x is the variable that we want to use, and so we're going to treat y as a constant. In other words, we're going to treat y just like it's any other number. So what I would suggest you do is take a second to rewrite this the way that you would rewrite it if y really was just a number. So in this case, I would say 3x squared. That's fine, there's no y's in there. But the second term, I don't ever really, if y was a number, I would never really write 2 times x times 7. That just looks weird. I would move the 7 around. I would just rearrange this and say it's 2 times 7 times x. I'd like to see a number times the power of x when I'm thinking of x as my variable. So instead of writing 2xy here, I would write 2y times x. And it's the same thing, but now I can really think of this as a number times x. And then I have minus y cubed. And there are no x's in this, so treating this like a constant is just going to be, you're treating it as if it's 1,000 or 100 or whatever, just any number at all here. So now when I take the derivative of this, the derivative of 3x squared is 3 times 2x, same rule we used before. The derivative of 2y times x, well, I'm treating the y like a number, so I'll have 2y times the derivative of x. The derivative of x is 1. And then I have minus y cubed. Well, if I'm really treating y as just a number, then I'm taking the derivative of a number that has no x's, and the derivative of that would be 0. So the hardest thing in this section is to get used to the idea of being able to, just in your mind, treat one of the variables as a constant. And that means treating it just like you would any other number. So I would simplify this. This is 6x plus 2y, and that would be my correct derivative with respect to x. So that's, you can either write f sub x, or I can write the derivative of z with respect to x. Similarly, if I want to find the derivative with respect to y, well, now I have to treat x as a constant, like it's a number. And so I'm back to the drawing board, and I'm going to rewrite this so that it looks like a number times the power of y. If y is my variable, then I want everything to look like a number times the power of y. Well, there are no y's in the first expression, so that's just going to be treated like any number. Here I have 2x times y. And again, I know I'm not really doing anything there, but I really want to see this as number times the power of y. And then the last term, it already looks like a number times the power of y. The number here is 1. It's 1 times y cubed. So it looks like a power of y already. So there's really nothing I have to do to this one to make every term look like a number times the power of the variable. But I do want to give that some thought. So as I go across here, the derivative, so again, derivative with respect to y now, the first term has no y's in it. And we know that if you just have a number with no y's in it, the derivative is 0. Here I have 2x times y. So the derivative should be 2x. I don't think about that as a variable. I think of it as just a number times the derivative of y is 1. And then finally I have the derivative of y cubed, which is 3y squared. So if I can hold that in my mind, that I want to treat the x's just like a number and the y is the variable, then I can get all the way through the expression correctly. The hard thing is that sometimes you'll sort of change your mind halfway through the problem about which is the variable and which is the constant. And that's why I like doing this rewrite first, so that the entire expression feels like a number times the power of the variable plus a number times the power of the variable, and so on all the way across. But I have to think about what the variable is and which letter I'm going to treat as a constant. Okay, so so obviously finding a particular value of the partial derivative is easy. That's just a matter of plugging in. So this is asking about fx, which was the first one we got. So putting x equals 1 and y equals 2 is easy to do. That gives me 4. But what I really wanted to show you here was the right way to interpret that. And to do that, I will go to the applet that's linked under Custom Contents. And so here's my applet. Well, this was an applet written by Paul Seeberger, not mine. But it's very nice for showing 3D things, and I want to illustrate for you what the value we just found represents. Remember, we said that one of the partial derivatives, I believe it was when x is 1, y is negative 1, we said that the partial derivative was 4. So let's look at what that actually means. First of all, I'm going to have to type in here the function that I'm using. So that was 3x squared plus 2xy minus y cubed. And we'll get a graph, and you can see it grows very quickly, so you can't see it all that well. But the nice thing is that I can identify a point on this surface very easily with this applet. We want to know the point where x equals 1 and y equals negative 1. So this picture over here on the bottom left represents the floor. I talked about the surface, remember, as you think of the x and y as a point on the floor, and then you look up to see the height of the surface, which is your z-coordinate. So if x is 1 and y is negative 1, that would be a point right here. On the applet, it shows you what that point would look like on the surface. So if you imagine yourself walking out to a point on the floor and then looking up above you, that's what you would see up there. So that's fine. That's what the point represents. What about the slope? Well, we said the slope represents the change in the z-coordinate for every 1 unit change. In this case, it will be in the x direction. So what I mean by that is, if you go 1 unit in the x direction, so we're starting here at 1, negative 1, and I go 1 unit in the x direction, what's happening is the graph is increasing 4 units at a rate of about 4 units in the z direction. So the z, remember, is the height. So I'm saying that as I go in the x direction 1 unit, I'm expecting my surface to go up 4 units in height. And so that's pretty steep. Right? 4 to 1 ratio is pretty steep. The applet also allows you to actually show a tangent line. So the fx tangent line means that I can actually see this as a line with slope 4. And so you can see how I can now visualize, really it's still slope of a line, but now the line is a line that's running up in the air in the z direction height instead of just on the xy plane.